Section: Introduction. In this section, we discuss the growing popularity of large language models, LLMs, across various fields due to their strong performance. However, deploying these large models on mobile devices and edge hardware is difficult because they require significant memory and computing power. This has led us to explore smaller language models, which we refer to as small-scale large language models, SLMs, typically with 2 billion parameters or fewer. These models are particularly useful in situations where cost and resource limitations are critical, such as on servers where reducing inference costs can help attract and retain customers. SLMs have shown impressive capabilities, often achieving competitive results despite their smaller size. We have seen techniques like pruning, quantization, and other optimizations that enhance their performance, allowing SLMs to match or even exceed the effectiveness of much larger models. For instance, the Gemma 2B model outperforms the much larger OPT-175B, challenging the idea that size alone determines a model's effectiveness. Additionally, SLMs can deliver fast, efficient, and cost-effective AI solutions without compromising on performance, making them appealing for organizations with limited budgets, such as small businesses and academic institutions. While previous research has mainly focused on optimizing SLMs for inference, there has been less attention on their training dynamics. This is an important area to explore, as the training demands for LLMs may differ from those for SLMs. Given the variety of hardware options available on cloud platforms, such as different GPU types and batch sizes, we recognize the need for a thorough analysis of how these factors influence the training efficiency of SLMs. We specifically look at practical metrics like cost per loss and tokens processed per second. Our findings suggest that for smaller models, more affordable options like a 100-40 GB GPS and distributed data parallel (DDP) setups can be effective without losing performance. In contrast, larger models require advanced configurations, such as A100 to 80 GB and H100-80 GB GPUs, along with techniques like flash attention and fully sharded data parallel to manage larger batch sizes and avoid memory issues. Recent developments highlight the necessity of scaling AI systems not just for top performance but also for real-world applications. The main contribution of our paper is to address the need for evaluating the computational challenges and cost-effectiveness of training SLMs with up to 2 billion parameters across different cloud infrastructures. We identify several key points. 1. Flash attention is more crucial for SLMs than for LLMs. 2. High-end hardware like H100 to 80 GB and A100 to 80 GB may not be cost-effective for SLM training. 3. DDP is the most effective distributed training method for SLMs. And 4. Maximizing GPU memory usage is not always the best strategy for cost-effective training. We aim to identify architectures that provide the best performance at the lowest training cost. While training costs are often measured in terms of time, iterations, or tokens, we believe these metrics are insufficient for budget-conscious infrastructure choices. We propose metrics that directly consider the dollar cost of hardware, focusing on maximizing model accuracy while minimizing costs, or in other words, optimizing for accuracy per dollar spent. Previous studies have established neural scaling laws that describe the relationship between accuracy, loss, and the number of training samples or tokens. In our work, we concentrate on the number of tokens processed during training and the associated costs. We derive the cost of processing tokens by averaging publicly available prices from various cloud providers for each hardware setup. Our analysis results in cost metrics that, when combined with loss scaling laws, can help identify the minimal cost needed to achieve a target loss. We also recognize that other metrics, such as CPU, GPU utilization and memory bandwidth usage, are important and will be explored in future work. We will present our findings on cost per token in various setups, where a value of 1,000 indicates that training 1,000 tokens costs $1. Section Summary. In this section, we discuss the growing interest in small-scale large language models, SLMs, as cost-effective alternatives to larger models, highlighting their competitive performance despite smaller sizes and the need for systematic analysis of their training dynamics on various cloud infrastructures. We emphasize the importance of optimizing training costs and efficiency, proposing metrics that incorporate hardware expenses to maximize model accuracy while minimizing training costs. Section: Model and Parameters. In this section, we focus on llama architectures, which are among the most widely used in recent public large language models, LLMs, and small language models, SLMs. The smallest versions, LLAMA2 and LLAMA3, have 7 and 8 billion parameters, respectively, making them too large for most mobile devices. We determine the number of decoder blocks and parameters for our models by fitting a curve to the llama models, which helps us define our own models. We evaluate 4 different model sizes with 100 million, 500 million, 1 billion, and 2 billion parameters. Importantly, we optimize all configuration parameters not shown in the figure's x-axis or legend. This involves conducting a comprehensive grid search over all combinations of configuration parameters, ensuring that each point in our plots represents the best configuration based on the specified parameters. We aim to find the optimal ratio of tokens to dollars and assume that tuning hyperparameters, like the learning rate, can lead to the best convergence with the hardware configurations. Next, we outline our configuration parameters. We assess 3 types of NVIDIA GPUs: A100 to 40 GB, A100 to 80 GB, and H100 to 80 GB, using bfloat16 data types across all GPUs. We explore 3 main training setups for each GPU type: single-node single GPU, single-node multi-GPU, and multi-node multi-GPU configurations. For setups with multiple GPUs, we evaluate distributed data parallel, DDP, and fully sharded data parallel, FSDP, communication methods. For FSDP, we examine 2 sharding policies: full sharding, where we shard all gradients, optimizer states, and weights, and grad_op sharding, where we only shard gradients and optimizer states while keeping the weights intact. We utilize RDMA, EFA for communication. We also investigate various sample sizes that can fit into a single GPU during training, fixing the sequence length at 1028 and adjusting the batch size. Since we cannot fit 128 samples into the memory of our smallest model, we test per device batch sizes of 4, 8, 16, 32, and 64, without using gradient accumulation. Additionally, we analyze the impact of using flash attention in the attention block. In our experimental results, we present findings from the A100 to 40 GB, A100 to 80 GB, and H100-80 GB GPS. We implement our models using Hugging Face and Run experiments with PyTorch, maintaining a sequence length of 1024. Each setup is tested at least 3 times, with 10 training steps each, and we report the average results along with error bars. We frame our findings as research questions and answers. For the first question, we explore the importance of flash attention during SLM training. Our results show that flash attention significantly enhances the token-to-dollar ratio, especially for smaller models, as the cost of attention grows with context length. For larger models, flash attention allows for larger batch sizes, preventing out-of-memory errors. For the second question, we assess the best GPU type for training SLMs given a fixed number of GPUs. While we don't see a consistent pattern across all models, the A100-80 GB GPU performs better when training larger models with many GPUs, allowing for larger batch sizes. For the third question, we investigate the best communication scheme for training SLMs across different node counts. Our findings indicate that DDP is preferable for smaller models due to lower communication volume, while FSDP outperforms DDP for the largest model, allowing for larger batch sizes. We also find that FSDP with gradient and optimizer state sharding has lower communication overhead than full sharding. Finally, for the fourth question, we analyze the best communication scheme for various global batch sizes. We observe that FSDP consistently outperforms DDP for the largest model and batch sizes, enabling training of larger global batch sizes compared to DDP, which leads to out-of-memory errors.